There's content about quark structures, strange particles, and also conservation laws, so it's quite a useful question. So straight off the bat, it's asking you to name two baryons. I'm just going to change the pen color, but the two baryons you need to know about are protons and neutrons. So those are enough to get you 2 marks in this case, which is the number of marks in this question. This next question is also a 2-mark question. Now, to find the quark structure of anything, I've laid out this sort of plan here of how we're going to approach this question. First of all, this is a pion, which is a pi meson. Mesons are made of one quark and one antiquark, so we know it's definitely this pair here. We're then going to think about the charge, baryon number, and strangeness of this pi particle. Pi plus particle, by the way, if you can't see the charge. So the charge would be +1. The baryon number would be 0 because only baryons have a baryon number of 1 and antibaryons have a baryon number of -1. The strangeness is 0, and we always assume that it's 0 unless it tells you otherwise in the question. So what combination of quark and antiquark gives you these 3 options here? Well, if we think about it, it's actually the up and anti-down quark. Now the reason for that? By the way, an antiquark just has exactly the opposite of everything that's for the quark itself. So the anti-down quark would have a +1/3 charge and a baryon number of -1/3. So the reason why this works out is because not only is a quark and antiquark pair, the charge will be 2/3e plus 1/3e if we take an antiquark, so add up to 1. The baryon number would be 1/3, take away 1/3, which is 0. The strangeness would be 0 plus 0, which is 0. So it matches and it checks out. So the K plus is a strange particle. Give one characteristic of a strange particle that makes it different from a particle that's not strange. So it's a K plus meson, by the way. Well, one unique characteristic of a strange particle is that it has a strange quark. Of course, if a particle is not strange, it won't have a strange quark. So that's enough to get you the mark for this question. One of the following equations represent a possible decay of the K plus kaon. By the way, kaons decay into pions. That's something that you need to know in the spec. So automatically we know that this can happen, whereas this can't happen. But that's not actually a valid reason. Let's talk about what we could say is a valid reason. And you want to think of conservation laws here. So I'm going to change the pen color again to a darker color. Let's look at this equation here. The 3 quantities that are always conserved are charge, baryon number, and lepton number. Strangeness is only conserved sometimes. So let's compare the charge, baryon number, lepton number for this second interaction. I'm just going to compare for the second one because I know that it definitely doesn't work out and I don't want to waste your time. So this is an antineutrino. The charge of this is 1. The charge of a positive muon is 1. The charge of an antineutrino is 0. So an antineutrino is massless and is chargeless. The baryon number of a K meson is 0. The baryon number of a pi meson, a muon, which is a lepton, is 0. And an antineutrino has a baryon number of 0. So that's conserved. Now lepton number. Is a kaon a lepton? No, it's not. So it has a lepton number of 0. Now a muon is a lepton, which is negatively charged. So an anti-muon would be an antilepton, meaning it'd have a lepton number of -1. Similarly, a neutrino would be a lepton. So an antineutrino would be an antilepton, so we'll have a lepton number of -1. So on the right hand side, this adds up to -2, and that's not balanced by the lepton number on the left hand side. So we say that this one's not possible as the lepton number is not conserved. Hopefully that made sense. Now on to the last question. I've written 2 very important facts from the specification that you need to know. The fact that strange particles are produced by the strong interaction where they're not conserved. Strangeness is not conserved, but when strange particles decay via the weak interaction, it's sometimes conserved. So that's why we don't really take into account when we're considering conservation. So it says that a strange particle X decays. So straight away, because it's strange and it's decaying, it has to be via the weak interaction. That's the answer to this question. And just a bonus question, but the exchange particle for the weak interaction is actually the W boson. It can be a W minus or a W plus depending on the question. Here it's a W minus. Thanks for watching. Hopefully that helped. Please like the video, comment, subscribe with post notifications on. I'll post a new video every day. And I've linked my email in the description if you want any tutoring inquiries. But thanks for watching. Have a good day.